Hello and welcome to this A-level chemistry video where I'll be telling you everything you need to know about Year 2 organic chemistry mechanisms. We'll be focusing in on nucleophilic addition, electrophilic substitution, and nucleophilic addition-elimination. If you want the Year 1 organic mechanisms video, that's available as a link in the description. The nucleophilic addition mechanism occurs when there is a reaction of an aldehyde or a ketone. And so this is something that's got a carbonyl group, which is that C double bond O, by itself, and so not with any other reactive atoms as part of its functional group. Remember that the word nucleophile is taken from the fact that the nucleus is positively charged, and so a nucleophile is positive seeking, and so that means that we've got something that is either negatively charged or partially negatively charged, and we might write delta minus to symbolize this. And so what happens in a nucleophilic addition mechanism is that a positive seeking species, the nucleophile, joins on to the carbonyl carbon atom. And the reason that this happens is that the carbon in the carbonyl group is partially positively charged, or delta plus. And this is because it's connected to the highly electronegative oxygen atom, which is more electronegative than the carbon, and so we get what's referred to as a negative inductive effect, where the electron density in the double bond between the carbon and the oxygen is pulled towards the oxygen atom, leaving the oxygen delta minus and the carbon delta plus. And so a nucleophile, that's something negative or partially negative, remember, attacks that delta positive carbon atom and forms a new bond to it. There are two examples of nucleophilic addition that you need to know, and they are the reduction of aldehydes and ketones to form alcohols, and to do that we use NaBH4 in aqueous solution, and that allows us to convert an aldehyde into a primary alcohol and a ketone into a secondary alcohol. And there's also the preparation of hydroxynitriles using KCN as the source of our nucleophile, followed by the addition of dilute acid in a solvent, which is usually water. In the alcohols topic, we learn that we can oxidize primary alcohols into aldehydes and secondary alcohols into ketones. With the nucleophilic addition mechanism, we can reduce an aldehyde and turn it into a primary alcohol, and we can reduce a ketone and turn it into a secondary alcohol. In order to do this, we need to use a reducing agent, and the one that we use for the reduction of carbonyl compounds is sodium borohydride, or sometimes called sodium tetrahydridoborate, but you can just use its formula NaBH4. Sodium borohydride is an ionic compound, and when it is dissolved in water to make an aqueous solution, it is a source of the hydride ion. And so it's really important that we know that the condition for this reduction is to use a water solvent. You need to be able to understand and recreate the mechanisms for the reductions of aldehydes or ketones back into alcohols. And these are called nucleophilic addition reactions. And the hydride ion from the reducing agent is the nucleophile. You need to remember that within the aldehyde or ketone, the C double bond O is polar, and that's because the carbon is electron deficient and the oxygen is more electronegative. And so the delta positive carbon is attracted to the hydride ion. And so what happens is the hydride ion attacks this slightly positive carbon atom and uses its lone pair to form a new bond between the carbon and the hydride ion. And that's down to the attraction between the two of them. This happens very readily. And that's what this first curly arrow is showing, the formation of a new bond between the carbon and the hydrogen. This would give the carbonyl carbon 5 bonds. It can only have 4. And so what happens is the bond between the carbon and the oxygen partially breaks. 2 of those 4 electrons are pulled by the oxygen away from the carbon, and the oxygen keeps them for itself. And that's what this second curly arrow is showing. Just as a note of caution, if you end up drawing your diagram a little bit too small, like I've done here, I choose to deliberately exaggerate the curl of that curly arrow, just so I can really demonstrate that it is starting from that double bond between the carbon and the oxygen and finishing at the oxygen, which is taking both of those electrons from that bond. This gives us a negatively charged intermediate because the negative hydride ion has added onto the aldehyde or the ketone, and we need to conserve the charge between stage 1 and stage 2. And that means that the oxygen that took both of those electrons from that double bond to the carbon is now going to be negatively charged because the hydrogen is now neutral because it used that pair of electrons to form a new bond. And so the final stage of this mechanism needs to show how we get from our negatively charged intermediate to the alcohol. And what needs to happen is the oxygen within this intermediate that is now negatively charged uses its lone pair to form a new bond to a hydrogen ion. And that's what this third curly arrow is showing, the formation of a new bond. Typically, that hydrogen ion is going to come from the solvent, from the water that the sodium borohydride was dissolved in. But sometimes we might choose to add a weak acid separately as a source of the hydrogen ion. And this will then produce our alcohol product, which, if we've been commanded to draw the mechanism, we don't need to show. But I'm showing it here just so we can see the full journey from aldehyde or ketone to alcohol. So I've been really generic with this mechanism, just using R groups to finish off the molecule. If we make this into ethanal, that means we'll have a CH3 group for the left-hand side R group and just simply a hydrogen for the right-hand side R group. That will, of course, then have a knock-on effect in the intermediate. It would look like this. And then the product that we produce would look like this. And so we can see that we started with ethanal and we've produced ethanol. And we could, instead of showing it as a mechanism, or maybe as well as that, we could represent this with an equation which uses structural formulas. So ethanal has got the formula CH3CHO, and ethanol is CH3CH2OH. And then to show the reduction, we are in fact allowed to just use a capital H for hydrogen inside square brackets to show that we are giving hydrogen from some kind of reducing agent without using the reducing agent's full formula. Just like we can do the same with a capital O for oxidation when we're using an oxidizing agent. And then to balance this, we actually need to put a big 2 as our coefficient in front of the hydrogen from the reducing agent because the aldehyde is gaining 2 hydrogen, 1 from the nucleophile and 1 from the solvent. And if instead of using ethanal, we used propanone, we would have 2 CH3 groups, either side of the carbonyl group at the beginning, which means we'd need to have 2 CH3 groups in our intermediate and 2 CH3 groups at the end. And so this time we would produce propan-2-ol. And we can show that in a second equation. We've got the structural formula of propanone, we've got propan-2-ol, and we're going to be needing to once again add 2 hydrogen from our reducing agent. That is always the case in nucleophilic addition. For reduction, we need to add 2 hydrogens from the reducing agent to turn our carbonyl compound into an alcohol. The nucleophilic addition mechanism can be used to produce hydroxynitriles. And hydroxynitriles are a family of organic chemicals that have got 2 distinct functional groups. First of all, we've got the nitrile functional group. And within the hydroxynitrile, the nitrile has got the highest priority because of that triple bond between the carbon and the nitrogen. And so that means that the carbon that is attached to the nitrogen is always treated as carbon number 1. There's also a hydroxy group, and this hydroxy group is always on carbon number 2. And because the nitrile has the higher priority, we refer to this as a hydroxy group rather than an alcohol group. And after that, the length of the carbon chain is what determines how this molecule is named. And so if we had a chain of 3, so we had a CH3 group in the position of this R group, we would refer to this as a nitrile, highest priority. The chain of 3 includes the carbon as part of the nitrile functional group, and so this is propane nitrile. Remember the convention that we need to have a vowel between two consonants in something's name. And then the hydroxy group is on carbon number 2, and so this molecule would be 2-hydroxy propane nitrile. In order to produce the hydroxynitrile, we need to react our carbonyl compound with potassium cyanide, which is an ionic compound, so in an aqueous solvent, which is what we use, it will fully dissociate into the cyanide ion, Cn-, and the potassium ion. And this, remember, needs to happen in aqueous solution, so it will dissociate readily. And then we need to follow this addition of potassium cyanide by the addition of dilute acid, which is the source of the hydrogen ion, which is needed for the second step of this mechanism. And so if we look generally, first of all, at a carbonyl containing compound, we've got a trigonal planar arrangement around that carbonyl group because there are 3 electron clouds repelling each other as far apart as possible. So that is a 120-degree bond angle. The first thing that happens in this mechanism is the cyanide ion, which is negatively charged, attacks the partially positive carbon atom in the carbonyl group. And so it uses the lone pair on the carbon atom within the cyanide ion to form a new bond between the carbonyl carbon and the carbon from the cyanide ion. And then this has a knock-on effect because the carbon that is in the carbonyl group would have 5 bonds if that was the only thing that happens. And that can't be the case. And so what happens is one of the pairs of electrons from the C to O double bond is pushed onto the oxygen from within the carbonyl group. And so that bond breaks partially, and so it's going to become a single bond with only 2 electrons in instead of a double bond with 4 electrons. This then moves into the formation of a negatively charged intermediate, which is mostly those 2 reactants bonded together. But because we need to conserve the charge from one stage of a reaction to the next, the oxygen that took that pair of electrons from the carbonyl double bond, it needs to be negatively charged because now the cyanide is neutral. And then to finish this mechanism off, the oxygen with that negative charge and the lone pair of electrons that it took from out of that carbonyl double bond attacks a hydrogen ion from the dilute acid. And this is the formation of a new bond between that oxygen and the hydrogen from the acid. And this then produces something that is neutral because we have 2 charged particles in our intermediate, one negative, which we must show in a mechanism, and one positive, which we also need to show. And we produce our 2-hydroxynitrile. Now, if in this mechanism we had used ethanal, that means we would have had a CH3 group in place of one of these R groups and a hydrogen in the other position. That means our intermediate would have looked like this. Again, we're just literally swapping those R groups out and the CH3 and the hydrogen in. And we do the same with the product. And you can see, in fact, that the first product that we have made is the 2-hydroxypropane nitrile from before. And we can represent that with the equation, with the ethanal in its structural formula reacting with the potassium cyanide in aqueous solution, remember, and then that converts into the 2-hydroxypropane nitrile and the potassium ion, which I'm including here because I'm using the full reagent in the reactants, but technically that potassium ion is a spectator ion because it's aqueous on the left and aqueous on the right. And the dilute acid, the H+, would also be added over the arrow, and that would be aqueous as well. I suspect you wouldn't be asked to include state symbols in an equation like this, and the reason is that the organic compound, that aldehyde or ketone, might be soluble in the aqueous solution, or it might not. The solubility of organic compounds, particularly carbonyls and alcohols and things with polar functional groups, that solubility depends on molecular size, with the longer groups becoming less soluble. So ethanal is likely to be soluble, whereas something longer, say hexanal, is likely to be insoluble, so it would have the liquid state symbol. But as I say, I suspect state symbols not required. If we did this mechanism on propanone, a ketone, we'd get a very similar reaction pathway. We're just swapping that hydrogen for a methyl group, and that's the same in the intermediate and the same in the products. But this time the product would have a different name. It would still be 2-hydroxypropane nitrile, but we also have a methyl group on that second carbon atom. And so this would actually be called 2-hydroxy 2-methylpropane nitrile, remembering that our branches need to be in alphabetical order. And then an equation for this reaction would look very similar to the aldehyde reaction. The only two changes are we're showing the structural formula for propanone instead of ethanal, and then we're showing our organic product as being slightly different to the 2-hydroxypropane nitrile. Now you can see that I'm giving priority to the nitrile by putting that in its normal form, and the methyl group along with the hydroxy group are shown as being in brackets. You could probably get away with that from the other way around, but I prefer to show the nitrile as being part of the core chain. That reminds us of its priority. When we do this mechanism, we use potassium cyanide, which has some associated hazards. And so it's really important to carry out a risk assessment. And so the hazard identifies the chemicals that could be dangerous or the parts of a practical that could be dangerous. And so in this case, potassium cyanide is the hazard. And then the risk tells us the nature of the hazard. Well, potassium cyanide is toxic, and it also produces hydrogen cyanide in the reaction. And so we need to take steps to minimize this risk, and this is by considering the control measures. Well, the toxic nature of potassium cyanide can be offset by storing it and handling it carefully. But the production of hydrogen cyanide is more of a danger, and so we need to make sure that we do this reaction in some kind of fume cupboard to prevent that hydrogen cyanide being released into the main part of the room. In addition, this mechanism produces some organic products which are flammable, and so the control measure here is to heat this reaction if you want to warm it to increase that rate of reaction, heat that up in a water bath or with a heating mantle. Definitely no direct flames. As an alternative to using potassium cyanide as our source of our nucleophile, we can actually use hydrogen cyanide instead. And when this reaction happens, the mechanism is exactly the same as for the potassium cyanide because we're still using the cyanide ion as our nucleophile. And the equations are really similar as well. There are a few key differences. Of course, the first one is that we're using hydrogen cyanide and we need to represent that in the equation. The second difference is that we aren't producing potassium as a spectator ion in the products. And then the third difference is we actually don't need to add an acid to our equation, and so we don't have H plus over the arrow. And the reason for this is that the hydrogen cyanide can be the source of the hydrogen ions as well as the cyanide ions because it is weakly acidic and it will dissociate into H plus ions and the cyanide ions as well. Overall, though, despite the toxic nature of KCN, KCN is preferred as the source of the nucleophiles because it is an ionic compound, which means in aqueous solution it will readily dissociate and produce a higher concentration of cyanide ions than you'd get with the HCN, which is only weakly acidic, so will only partially dissociate. In addition to that, hydrogen cyanide is a gas, so it is much harder to handle and store than the KCN. So overall, KCN is definitely preferred. When you carry out nucleophilic addition reactions on aldehydes and unsymmetrical ketones, for instance ethanol or butanone, you produce a mixture of enantiomers. Having two enantiomers means that you've got two molecules that are mirror images of each other. But more than that, they are non-superimposable when you turn one of them around. Another way of referring to enantiomers is to call them optical isomers. And you get optical isomers when there is at least one chiral carbon within a molecule. And a chiral carbon is a carbon atom in the molecule that has got 4 different groups attached to it. And these optical isomers will rotate plane polarized light, either in a clockwise direction or an anti-clockwise direction. Even though this mechanism produces 2 enantiomers, there is no overall optical activity, as the product is a racemate, sometimes known as a racemic mixture. And this is where you have an equal mixture of the 2 different enantiomers. And so there is no optical activity, since the rotation of plane polarized light, either clockwise or anti-clockwise, will cancel each other out precisely. This racemic mixture comes about since the molecules with the carbonyl groups are planar in the region around the carbonyl carbon. And so this means that when the nucleophile attacks, the cyanide ion in this case, the attack is either going to be coming from above the carbonyl group or below the carbonyl group. And since both of these attacks are equally likely, you will get 50% of the nucleophilic attack occurring from above the carbonyl group. And this will produce one of the 2 enantiomers, and 50% of the nucleophilic attack occurring from below the carbonyl group. And this will produce a different enantiomer. And this means that we end up with an exactly 50-50 attack angle, and so we end up with an exactly 50-50 mixture between the 2 potential enantiomers that could be produced as a result of this nucleophilic attack. The electrophilic substitution mechanism occurs when there is a reaction of a benzene ring. And not just a benzene ring being present, the ring itself needs to change. We can represent the benzene ring with the hexagon with the circle inside it for the delocalized electron cloud, or we can just use the formula C6H6 for the benzene ring, but obviously if there are groups already on the ring, it won't be C6H6. And what occurs, in simple terms, is one negative seeking species replaces another. And in electrophilic substitution, it's always an H+ ion that is replaced. Now, an electrophile, if we break that word into 2 pieces, is something that is negative seeking. And so really what we're talking about is something that is a positive ion or something that is electron deficient, delta plus. Why does it happen? Well, the pi cloud of delocalized electrons in the center of the benzene ring is electron rich, and therefore it attracts the positive ion or the electron deficient atom in the electrophile to itself. There are 2 types of electrophilic substitution mechanism that you need to know about. There is nitration, which involves concentrated nitric acid, HNO3, as our source of our electrophile, and it involves a concentrated sulfuric acid catalyst. There's also Friedel-Craft's acylation, and the electrophile comes from an acyl chloride, and we use an aluminium chloride catalyst. This reaction is very slow at room temperature, so we need to do this under reflux in the presence of a dry ether solvent. There are other choices, but it's really important that we have a non-aqueous solvent. In nitration, the electrophile comes from the nitric acid in a reaction with the sulfuric acid catalyst. And this is actually an interesting reaction as it's happening between two acids. But since the sulfuric acid is a stronger acid, the nitric acid therefore acts as a base and accepts one of the sulfuric acid's protons. And so in step 1, we end up producing H2NO3+, which is the conjugate acid to nitric acid's base. And we also produce HSO4-, which is the conjugate base for the sulfuric acid. And then in step 2, the H2NO3 breaks apart into the nitronium ion, which has got the formula NO2+, and this is our electrophile, and we also produce water. This reaction can be shown in 2 steps, as I've done at first, or we can combine it into 1 step, where we've got the nitric acid reacting with the sulfuric acid, as before, going straight through to the nitronium ion electrophile and the water and the HSO4-. In the mechanism itself, it's important to remember that the delocalized pi cloud of electrons is electron-rich. There are 6 electrons in it, 1 electron from each of the carbon atoms. And so it is attracted to the positive electrophile, the nitronium ion. And the electrophile attacks the benzene ring, and we show this using the curly arrow that I'm showing now. Now, curly arrows, remember, always show the movement of electrons, and that's what we're showing here, but we must say that the electrophile attacks the benzene ring. And the symbolism of this curly arrow is that we're showing that a new bond is forming between the carbon atom and the nitrogen atom from the electrophile. And then this moves on through to make an intermediate chemical that I'm showing here. Now, there's 2 really important features of this intermediate. First of all, the delocalized pi cloud has been partially broken because those 6 electrons have now become 4, because 2 of the electrons in that pi cloud are now involved in the bond between the carbon and the nitrogen. And so there's only 4 electrons there. And so the ring that was representing all 6 of those electrons needs to be incomplete. And so what I'd like you to do is imagine that there was a line across the benzene ring dividing it 2/3 on one side and 1/3 of the other. And so the benzene ring's delocalized pi cloud now cannot extend beyond this purple line. And so that's why I've got an incomplete circle now to show that we've got 2/3 of the electrons that we had before. Not only that, it is now positively charged. And this also makes sense from the point of view of conservation of charge, because the reactants were positively charged because of the electrophile. We've only got 1 intermediate now, and we need to conserve that charge, and we need to have a positive charge showing in that benzene ring. And so the benzene is unstable because it's positively charged, but it regains its stability by taking those 2 electrons back. And it takes them back from the bond between this carbon atom and this hydrogen atom. And so we show a curly arrow like so. And this curly arrow is symbolizing the bond breaking and the 2 electrons from that bond going back into the pi cloud. And so we produce this compound, which would be referred to as nitrobenzene, and we produce the hydrogen ion that has been replaced by the nitronium ion. If you've been asked to simply draw the mechanism, you just need to show this section. We don't need to show the structure of the organic product unless we've been explicitly commanded to do so. Now, that hydrogen ion that's been replaced is far too reactive to exist by itself. And so what happens is it reacts with the HSO4- that was produced during the generation of the electrophile. And this produces H2SO4, which was our original catalyst. So in this way, our catalyst has been regenerated and can be used again, which is part of the definition of a catalyst. If we want to make sure that we only add 1 nitro group to our benzene, we need to make sure when we're warming it up in this reaction that we keep the temperature below 55 degrees C. If we go above 55 degrees C, the temperature rise means that multiple substitutions occur, and so we get more than one nitro group joining the benzene ring, and we could get as many as 3 being added. This allows us to produce all sorts of different nitro compounds that have got huge range of uses in things such as pharmaceuticals and dyes and explosives. By far the most famous nitrobenzene compound is TNT, which has got 3 nitro groups because we've had substitution occurring 3 times with this methyl benzene. In addition to knowing how the electrophilic substitution mechanism occurs, you also need to know the mechanism for the generation of the electrophile, the nitronium ion. And this is formed through a reaction between concentrated nitric acid and concentrated sulfuric acid, and it takes place over 2 steps. The first step is the reaction between the nitric acid and the sulfuric acid, where the nitric acid uses one of the lone pairs on the oxygen atom that has the hydrogen attached, and it actually attacks one of the 2 hydrogen atoms of the sulfuric acid. And this curly arrow that I'm showing here is showing the formation of a new bond between this oxygen atom and this hydrogen atom. Of course, hydrogen atoms can only have one covalent bond, and so that means the covalent bond between this oxygen and this hydrogen atom needs to break, and that's what I'm showing with the next curly arrow. The pair of electrons in the covalent bond here is being taken completely by this oxygen atom. And this leads us to 2 intermediate products. This one is effectively H2NO3+, but I'm showing it in partial displayed formula here, so you can see that we've got a positive charge on this oxygen, recognizing the fact that this oxygen atom has used one of its lone pairs to form a coordinate bond here. In addition to that, the other product is the HSO4- ion, negatively charged, because this oxygen atom took both electrons from the covalent bond that it had previously been sharing with this hydrogen atom. And it's this HSO4- ion that goes on to accept the H+ that is substituted out of the benzene ring. Meanwhile, this H2NO3+ ion is involved in step 2, where actually all that happens is it falls apart into 2 pieces. And to do that, the covalent bond between the oxygen atom and the nitrogen atom, as I'm showing here, breaks. And it's the oxygen atom, with it being positive at first, that takes both of those electrons from out of that covalent bond, taking them away from the nitrogen, and this oxygen becomes neutral. And in fact, what it becomes is a water molecule, which is why the generation of the electrophile produces 1 molecule of water. Meanwhile, the nitrogen, which had its electrons taken away from the covalent bond in step 2, is now positively charged. And this NO2+ is the nitronium ion, the electrophile for this mechanism. During Friedel-Craft's acylation, the electrophile is generated from an acyl chloride. There are obviously a huge range of acyl chlorides, but what they all have in common is they have this carbonyl group and a chlorine attached to the same carbon. And on this occasion, I'm showing a chain of 2 carbon atoms, and so this acyl chloride would actually be called ethanoyl chloride. Acyl chlorides themselves are actually weak electrophiles, but we actually convert it into something different, which is a stronger electrophile. And so if we show an equation for the generation of the electrophile, we start with our acyl chloride, and it reacts with something that is referred to usually as a halogen carrier. And that's got a really important role to play here, because what it does is it interacts with one of the lone pairs on the chlorine atom in the acyl chloride. And it's able to do this because the aluminium in aluminium chloride is actually electron deficient. It's only got 6 electrons in its outer shell. And so what it's able to do is accept a lone pair of electrons from the acyl chloride. And as that lone pair of electrons is pulled away from the chlorine as part of the acyl chloride in turn pulls electrons away from the carbon that is bonded to the oxygen within the acyl chloride. And so we can show this with curly arrows. We can show the curly arrow between the lone pair on the chlorine and the aluminium. That's showing a new bond is forming. And then we can show a curly arrow from the carbonyl to chlorine bond being broken, and the chlorine is taking both of the electrons within that bond. And importantly, this produces something referred to as an acylium ion. And this is a carbocation that's been generated as a result of this, and it is a much stronger and more stable electrophile than the acyl chloride that we had originally was. And not only do we generate the acylium ion, our electrophile, we produce AlCl4-. The mechanism for Friedel-Craft's acylation is really similar to nitration. In step 1, our benzene ring is attracted to the electrophile, the acylium ion. And so the acylium ion attacks the benzene ring and a new bond forms, which we're showing with this curly arrow here. This leads to the formation of a positively charged intermediate, exactly the same as in nitration. And this is unstable because the delocalized pi cloud only has 4 electrons in it instead of the 6, which it needs to be considered stable. And it's also positively charged. And so it regains its stability by breaking the bond between the carbon and the hydrogen and taking those 2 electrons back into the pi cloud, topping it back up to 6 electrons, which is what it needs to become stable. And this turns into our acylated aromatic compound, which, if we'd used ethanoyl chloride, would actually have been called phenylethanone. And not only do we produce that, we also produce our hydrogen ion. As before, you wouldn't need to show this as part of the mechanism, but it's important to have awareness of what we're producing in this mechanism. And also, as with nitration, the catalyst is regenerated by reacting with the hydrogen ion that has been replaced. And so the hydrogen ion, which is highly reactive, reacts with the AlCl4- that was produced when we made our electrophile in the first place, and this turns into AlCl3, that's our catalyst being regenerated, and also HCl. And so in Friedel-Craft's acylation, as well as our phenyl ketone, phenylethanone in this case, we also produce HCl as a byproduct. And so in general, in electrophilic substitution, there are always 2 steps. And in each of those steps, there is just one single curly arrow. And we also need to remember that there is a positive intermediate in any electrophilic substitution mechanism. The nucleophilic addition-elimination mechanism occurs when there is a reaction of the carbonyl group in one of a number of chemicals. And these are acyl chlorides, where there is a chlorine attached to a carbonyl group, acid anhydrides, where there is a second carbonyl group connected to the first by a bridging oxygen atom, and an ester, which has got the carbonyl group connected to an oxygen and then a carbon chain. You can recognise that a nucleophilic addition-elimination mechanism will occur when you see that it's a reaction of the carbonyl group in one of these 3 chemicals. What actually happens in a nucleophilic addition-elimination mechanism is a positive-seeking substance, the nucleophile, attacks and joins onto the carbonyl carbon atom, which will be electron deficient. And so this is the addition stage of the mechanism. And then the elimination stage of the mechanism is where part of the original organic molecule then leaves. This mechanism occurs because the carbon in the carbonyl group is electron deficient. And this is because it's actually connected to 2 electronegative atoms, the oxygen and sometimes another oxygen or a chlorine. Both of these atoms are more electronegative than the carbon, so they pull the electron density from the covalent bond towards themselves, leaving the carbon delta plus and the oxygen and the chlorine delta minus. And so the nucleophile attacks the carbonyl carbon and forms a new bond to it. As well as knowing which organic molecules will undergo nucleophilic addition-elimination, you can also recognise that this mechanism might occur depending on the nucleophile. There are 4 that you need to know about. First of all, we've got ammonia, which has got the lone pair on the nitrogen, which enables this to act as a nucleophile. We've also got amines, which also contain nitrogen, and we can have a carbon group of any different length. And then we've got water, which has got the oxygen, which has got the lone pair that enables this to act as a nucleophile. And then we have alcohols last of all. Normally, we would see methanol as the nucleophile. There are so many different nucleophiles that can take part in nucleophilic addition-elimination and a number of different organic molecules that they can attack. So what we're going to do is we're going to look at an overview of the process first by looking at, in general, how nucleophiles might attack an acyl chloride or acid anhydride. And this generalization is useful because all of the nucleophilic addition-elimination mechanisms occur in the same way. If I generalise and I use my acyl chloride or acid anhydride or my ester represented in this way, where we've got the carbonyl group and the carbon chain, and we've got L representing the rest of the molecule, which might be a chlorine, it might be an OCH3, or it might be the rest of an acid anhydride. This together is generalised and referred to as a leaving group, so I'm giving it the symbol L. The nucleophile that could attack this compound will always have at least one hydrogen atom in it, so I'm going to use nuc to represent the nucleophile, but I'm also going to show one of the hydrogens for a reason that will become clear. The nucleophile must also have a lone pair on it, which will donate in the reaction, so I'm showing that lone pair as well. The first stage of the nucleophilic addition-elimination mechanism is the formation of a new bond between the nucleophile and the carbonyl carbon. The nucleophile is positive seeking and it is attracted to the electron-deficient carbon, and so it forms a new bond to it. This would give that carbon atom 5 bonds, and it can only have 4, so 2 of the 4 electrons in the carbonyl double bond are pushed towards the oxygen, and so that double bond effectively breaks and becomes a single bond. This organic starting material that would have been trigonal planar around that carbonyl carbon has now been converted into a tetrahedral intermediate substance. And you can see that we've got the nucleophile now connected to the carbonyl carbon. We've got now a single bond between the carbon and the oxygen that it was doubly bonded to. And we've now got a lone pair on that oxygen, which we need to show, because that represents 2 of the electrons that were in the double bond that oxygen now has sole ownership of. As a result of it taking those 2 electrons away from the double bond, it will now have a negative charge, and it's really important that we show that negative charge. In addition to this, the nucleophile has donated its lone pair of electrons to the carbonyl carbon, and so now it will carry a positive charge, and we need to show that on the nucleophile. And so what we've got is our tetrahedral intermediate, which we do show as being planar, being flat, just because it's easier to draw this way, but it is tetrahedral, and we've got a positive charge and a negative charge within it. This then moves us on to the elimination step of nucleophilic addition-elimination, because 3 things happen all at once. The lone pair on the oxygen goes back into where it was the double bond, and a new bond forms between that carbon and the oxygen, and we now get our double bond back again. That would give the carbon 5 bonds again, but what happens instead is the bond between the carbon and the leaving group breaks, and the leaving group, whatever it might be, takes the pair of electrons from that bond and has them for itself. And then the nucleophile, which was positively charged, takes a pair of electrons from the bond inside what was the original nucleophile, and part of that nucleophile takes that pair of electrons and brings it towards itself and the hydrogen that was in the bond within that nucleophile is now leaves, and we get what's referred to sometimes as deprotonation occurring as a result of this bond breaking. And so at the end of the reaction, we've got our acyl group with the majority of the nucleophile now attached to it. And then we've got our leaving group, which would be negatively charged and have a lone pair of electrons, and we've got the hydrogen that was lost as a result of the deprotonation. These two ions would come together and produce a separate molecule, which would be the byproduct. This is my preferred way of showing nucleophilic addition-elimination mechanisms, but there is an alternative which takes place over 3 stages. The first stage is identical because we have the addition part of the mechanism where the nucleophile attacks the carbonyl-carbon and the double bond partially breaks. Then elimination occurs in its own step where the oxygen reforms the double bond to the carbon and the leaving group leaves, taking that pair of electrons with it, so it is eliminated from the molecule. But the deprotonation occurs in a separate step. So we've got our organic intermediate here, which has still got a positive charge on the nucleophile, and so what happens in this stage is the bond between the nucleophile and the hydrogen breaks, the nucleophile takes both of the electrons from the bond, and the hydrogen leaves as an H+, and again we'll end up at the same product, but this has just taken place over an extra step. And so for me, I prefer to do it over just 2 steps because I think this makes life easier and I think it takes less time. This mechanism has a lot in common with nucleophilic addition, unsurprisingly because of its name. Nucleophilic addition also in stage 1 has the exact same curly arrows. The difference between addition and addition-elimination occurs where the nucleophile in addition is always going to be negatively charged, and so that means the intermediate in nucleophilic addition will always simply have the 1 charge of being negative on the oxygen. And so the intermediate is nearly the same as well, but not quite because you won't have this positive charge on the intermediate. And then the elimination part of the mechanism has a lot in common with simple elimination, and the biggest similarity is the number of curly arrows for my elimination here is 3 in my step 2 for my top mechanism, and in regular elimination from alcohols or halogenoalkanes, the elimination step there also has 3 curly arrows in it. Acyl chlorides react vigorously at room temperature with ammonia. And so if I had methanol chloride reacting with ammonia, the first step of the mechanism would be the ammonia donates its lone pair to form a new bond to the carbonyl carbon that it was attracted to because that carbon was electron deficient. And then the oxygen takes 2 of the 4 electrons from the double bond that it shared with that carbon atom, and this produces our intermediate, which has got the nucleophile now connected to the carbonyl carbon, and the nucleophile will be positively charged because it's used its lone pair to form a new bond. The oxygen that was part of the carbonyl group originally is now going to be negatively charged because it took 2 electrons out of that double bond, and it needs to be shown as a separate lone pair now on the oxygen. And then I'm showing one of the bonds between the nitrogen and the hydrogen as being separate, and I'm showing it on display because what's going to happen now is that bond is going to break and the nitrogen is going to take both of the electrons from the pair. You can see that I've drawn my nitrogen and hydrogen quite close together, so I'm exaggerating this curly arrow to make it really obvious that it's starting from the bond and finishing on the nitrogen atom. In addition, we remake our carbonyl double bond because that lone pair goes back into the area between the carbon and the oxygen, and we get a new bond forming, and the chlorine takes the electrons from the bond that it shared with the carbon, and that leaves and it is eliminated along with the hydrogen. And so the HCl is eliminated from this molecule, And then the acyl chloride derivative produced in this instance would be an amide, because the ammonia has formed on the same carbon as the carbonyl group, and so we've now got a carbonyl group and an NH2 on the same carbon, and this is the amide functional group. And you name amides by simply having methan, ethan, propan in front of it. And so since I was using methanoyl chloride in my example here, I would produce methanamide. And we can use an equation to represent this reaction as well as a mechanism. And so this is the structural formula of methanoyl chloride, and it's reacting with ammonia, and we produce our methanamide, and the HCl is eliminated, and we would observe misty fumes. And with acyl chlorides, the second product is always HCl, so we would always observe these misty fumes of the toxic HCl gas. Acyl chlorides also react vigorously at room temperature with primary amines, and the mechanism is identical to when ammonia reacts, but we produce something different in this case. And so the first step is the attack of the nucleophile on the carbonyl carbon. That lone pair forms a new bond between the nitrogen and the carbon, and the bond between the carbon and the oxygen partially breaks, with the oxygen taking both electrons from the bond. Then we produce our intermediate, which needs to have a negative charge on the oxygen and that lone pair, and the nucleophile is now attached to the carbonyl carbon, but it will be positively charged because it's used its lone pair to form this new bond. And so in stage 2, the bond between the carbon and the chlorine breaks and the chlorine leaves, and the oxygen uses that lone pair to remake the bond between the carbon and the oxygen, and that now becomes a double bond again. And from within the part of the molecule that was the original nucleophile, the positive charge is stabilized because the nitrogen takes the pair of electrons from the bond that it shared with that hydrogen, and the hydrogen is eliminated as an H+ ion. And so we produce this organic product, which would be referred to as an N-substituted amide on this occasion. And so it's called this because we've got something that looks really similar to an amide. If this CH3 group wasn't there and was an additional hydrogen instead, this would be an amide. But because we've got a methyl group, it needs to be a substituted amide. And because the methyl group is attached to the nitrogen, we use the nitrogen as a position indicator, just like we might a 1, 2, 3 in a complicated name. And so an N-substituted amide has got a carbon chain attached to the nitrogen. So in this case here, when we're naming our N-substituted amide, we should always name the amide part first. And so we've got a carbon chain of 2, so this would be ethanamide. But we've got a methyl group attached to the nitrogen as well, and so this would be N-methyl ethanamide. And remember, we make our 2 ions as a product, which would come together to make HCl. So we would refer to this as having eliminated HCl from the molecule. In terms of an equation, we've got our ethanoyl chloride structural formula here. It's reacting with the methyl amine, and we're producing our N-methyl ethanamide and the HCl. Acid anhydrides undergo the nucleophilic addition-elimination mechanism in the exact same way as acyl chlorides. Firstly, the nucleophile uses its lone pair to form a new bond with the carbonyl carbon, and it attacks it because the attraction is there between the partially positive carbon and the nucleophile. The electrons in the double bond are then taken partially by the oxygen, so that double bond is broken and becomes a single bond. This then gives us a charged intermediate with the nucleophile now attached to the carbonyl carbon and being positively charged because it's just used its lone pair to make a new bond. The oxygen, remember, is negatively charged, and we need to show that charge along with the lone pair that it's now got, having taken it from the carbonyl bond. That lone pair is then used to form a new bond between the carbon and the oxygen. We're reforming that double bond, and then the rest of the acid anhydride is now the leaving group, and so we've got a bond between the carbon and the oxygen which is going to break. The oxygen is going to take both of those electrons and leave this organic molecule. And the nucleophile part of the organic molecule needs to have its charge stabilized, and so that oxygen will take both of the electrons from one of the covalent bonds that it had, and it will take it from that hydrogen atom because that bond is easier to break, and so the hydrogen atom will also leave this molecule, and it will combine with the rest of the acid anhydride that left this molecule, and we will see the formation of a carboxylic acid. And in this case, because I was using ethanoic anhydride, we would produce ethanoic acid as a byproduct. The acyl derivative that we produce on this occasion, because I was using the alcohol methanol, would make an ester, and it would be a methyl ester because we've only got one carbon in the alcohol that attacked the ethanoic anhydride. And so this ester would be called methyl ethanoate. Remember, whenever you name an ester, you take the beginning of the name as how many carbons are in the alcohol, and the end of the name is to do with how many carbons are in the ethanoate or the propanoate part of the functional group. And as an equation, the structural formula of acid anhydrides looks a little bit odd. What we do is we show the part of the anhydride that is duplicated inside brackets with a 2 after it, and the oxygen, which effectively bridges these two groups together in the molecule, is shown outside those brackets. And so this is the structural formula of ethanoic anhydride. And then it's reacting with methanol, and we produce our ester, methyl ethanoate, and our ethanoic acid as our second product. Acyl chlorides react very vigorously with cold water, and the mechanism is nucleophilic addition-elimination. The water is the nucleophile, and it uses its lone pair to attack the carbonyl carbon and add on to this molecule. And the carbon has its bond that it's sharing with the oxygen partially broken. The oxygen takes both of those electrons from one of those bonds, and we end up producing an intermediate where we need to show that lone pair now on the oxygen instead of in that double bond, and the oxygen will be negatively charged. Additionally, the nucleophile has used its lone pair to make a new bond, so now it will be positively charged. What happens in stage 2 is the elimination. That double bond between the carbon and the oxygen reforms using the lone pair that the oxygen temporarily took out of the bond. Then the chlorine is going to leave, taking the pair of electrons that it was sharing the carbon away with it. The nucleophile needs to achieve stability, so it breaks its bond between the oxygen and one of the hydrogens and takes both of the electrons onto the oxygen, thereby stabilizing that positive charge, and the hydrogen leaves as a positive ion and the chlorine leaves as a negative ion, and so we end up producing hydrogen chloride, HCl, which we would observe as misty fumes during this reaction. The second product in this case would simply be a carboxylic acid. And since I've been showing methanoyl chloride at the beginning, the carboxylic acid that would be produced would be simply methanoic acid. And so the equation for this reaction would have methanoyl chloride reacting with water and producing methanoic acid and HCl. In summary, when carrying out acylation, you can use either an acyl chloride or an acid anhydride, and you'll get the same acyl derivatives. But remember, the acyl chlorides are much, much more reactive. There are some common nucleophiles that you need to be aware of. If you used ammonia, we would produce an amide. If you used a primary amine, you would make an N-substituted amide. If you used an alcohol, you would produce an ester, and if you used water, you would produce a carboxylic acid. The only difference in the mechanism and the equation really is the byproduct, which could be HCl for the acyl chloride, or it could be a carboxylic acid if we'd been using an acid anhydride. So these are the most common nucleophiles that you're likely to encounter for this mechanism, but in theory, anything that's got an alcohol or amine functional group in it could react as well. And so this is particularly common in industry when making drugs such as aspirin, and so you need to be on the lookout for anything that might have an amine or an alcohol functional group. Okay, that's the end of this video. Thanks for listening.